All right, so when we write our electron configurations, and we've seen how we can use the little Christmas tree diagram to do that, we can also represent our electron configurations using the orbital diagrams. Okay, so obviously here, if you needed to draw these, it would be sort of in a vertical graph-like thing. However, the way we can also show these are in a more horizontal way. So we can say, for instance, if I go from left to right now in order of increasing energy, I can say this is my 1s, this is my 2s, and then I have my 3 of the 2p's right next to each other like this. Okay, so these would be collectively the 2p. So in the case of oxygen, for example, the oxygen has a total of 8 electrons. First 2 electrons go into the lowest energy level. We have our 1s2. Then we have our next couple of electrons fill the 2s, 2s2. That's 2 into 4. Then 5, 6, 7. We do them individually according to Hund's rule, and then the 8th gets paired up. So this then would be 2p 4. What you'll notice so again, this here would be an increasing energy this way from left to right, right? As opposed to going from the left side here from bottom to top, which is the typical way, you'll also see being written this way. So a couple of things to note about the oxygen and also for the fluorine that we'll see after is that when you draw your orbital diagrams, for instance, and if you see any of these unpaired electrons, okay, that gives the atom a particular property. And what it means then, when we see these unpaired electrons, leads to a phenomenon called paramagnetism. Magnetism. We say that the oxygen then would be paramagnetic, in other words. And what that means is that that particular substance will be attracted to a magnetic field. And you can actually test this, using equipment, for example, to confirm the magnetic characteristic or property of an atom. And specifically now, this is due to the electrons, right? Remember, when you have these electrons that are spin up, right? You can think of the spinning charge as having a magnetic field north and south, right? They sort of amplify each other. That leads to that magnetic field, and then it will be attracted to that magnetic field if there's an external one. And that's in contrast to a one that is not attracted to a magnetic field, which would be ones where all of the electrons are paired, and we call that diamagnetic. So where all of the electrons are paired up, we have diamagnetism. Okay, and instead of being attracted to a magnetic field, your diamagnetic substances are actually repelled by a magnetic field. So again, a property or characteristic of a substance that is inherently linked to the electrons, and specifically whether those electrons are spin up, spin down, whether they're paired up, for example. Okay, let's take a look now at an example of how we write the electron configuration, and we'll pick let's do a different one. So your book, goes through several examples. Let's do electron configuration for, and again, you always have a periodic table. Let's choose potassium, which has the symbol K. All right, so the first thing you want to do is you want to locate that element on the periodic table. So potassium K is over here. And then right away, we can see how many electrons we're dealing with, right? So we focus in potassium atomic number 19. So we're dealing with 19 electrons that we need to configure. Okay, so according to our little Christmas tree diagram that we have here, I'm going to put potassium uh, right next to it. So K, so we have 19 electrons. We're going to start with the 1s, right? So we go 1s. How many electrons can fit in the 1s? Well, we're going to fill that with the two electrons, right? Only 2 electrons fit into the s sublevel because the s sublevel only has one orbital, which is an s orbital. All individual orbitals can only hold a maximum of 2 electrons. After that, we go to the 2s. Okay, we fill that with 2 electrons as well because we just have one of that s orbital, which can only hold 2 electrons. Then we go to the 2p. Okay, the 2p sublevel has 3 p orbitals, each of which can hold 2 electrons. Okay, so 3 of those p orbitals times 2 gives me a total of 6. So I'm going to fill that completely with 6 electrons. Then I go to the 3s. The s, just like any other s orbital or s sublevel, can only hold 2 electrons. Then I go to the 3p. Just like the 2p, the 3p can hold a maximum of 6 electrons because the 3p sublevel has 3 individual p orbitals, each of which can hold 2 electrons. So let's take a quick check here. We have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. I have one more electron. That electron is going to go into the next energy level here, which is the 4th energy level, and specifically the 4s. I just have one electron remaining, so it'll be 4s1. So this is your electron configuration for the potassium atom. And if I were to draw the orbital diagram, I can draw it like this. I have my 1s with 2 electrons in it. Those are my 2 electrons. That's my 1s2. Then I have my 2s2. Okay, 2 electrons in it. Then I have my 2p6, and you can just make a big long box, separate it into 3. So there's my 2p. I have 1, 2, 3, 4, 5, 6. Right, let's just cross these out as I go through 2p6. Then I have my 3s2. That's a single box, a single orbital. I have 2 electrons in there. That's my 3s2. My 3p6. So again, big long box with 3. Break it up into 3. That's my 3p. Each of these boxes is one of the p orbitals, and I have 6 electrons in there. So 1, 2, 3, 4, 5, 6. That's my 3p6. And then my 4s1. So 4s, just a single s orbital, and then 1 electron in it. And that's it. This here is your electron configuration. Okay, where you just have the 1s2, 2sp, etc. The box thing here, this is your orbital diagram. Okay, so those are the 2 different types of ways we can represent the electrons via the most efficient way, which is the electron configuration, or we can use the orbital diagram. And you can see now from the orbital diagram for potassium, we have one unpaired electron that we have there. So then we can say that would be paramagnetic, just based on the one unpaired electron. Okay, so to do this, what I'm using is our little Christmas tree diagram that we have here. I did mention earlier that we can actually use the periodic table to help us figure that out. Okay, so before we get to that, let's use potassium and let's show you now how we can condense this configuration. Okay, so we'll say using potassium, we can write a condensed, or what's known as a noble gas configuration. Okay, and the way that this works is, if I wanted to write the condensed configuration, I'm going to find my element in question first, which is potassium. Then I'm going to go backwards in the periodic table. Okay, so the backwards mean now the lower atomic numbers, and I'm going to find the noble gas right before it, immediately preceding it. So what's the noble gas immediately before potassium? So I have to go back to the next row, and I end up with argon, Ar. So what I can do now is I can say, and I can put argon, that noble gas, in square brackets. And by doing that, guess how many electrons I'm automatically accounting for? I'm accounting for those 18 electrons in argon, which are these 18 electrons that I have here, right? Count them up, you'll see that they're 18. So by doing this, and again, this only works with the noble gases. It doesn't work with only any of the other groups. I've accounted for 18 of those electrons. What's remaining then is the 4s1, and then I just write that right after it, like so. So this is the same. This is the electron configuration for potassium. Okay, and it's a much quicker way to come up with the same as opposed to this is the full electron configuration, where we start with the 1s2, 2s2, etc. This one here in green, this is the noble gas configuration or the condensed configuration. Okay, if you're not specified which configuration to write, you can use either. If it asks you for the noble gas, this is the one that you want to use. If it asks you for the full, well, you have to start with the 1s and work your way to the number of electrons in question. So what this brings to the forefront is that when we do write our electron configurations in either any of these ways, what we find is that we can condense it into the noble gas configuration, and these 18 electrons in the case of potassium, those represent, we'll highlight these in yellow here. These represent the noble gas core electrons. Okay, so these are the noble gas core electrons. And the remaining electrons, and highlighted on the orbital diagram as well, okay, all of these are the noble gas core electrons. The remaining electrons, in this case, there's just one electron, which is the 4s1. Okay, that is known as the valence electron. Valence electron is the outermost electron. They are found in the outermost occupied subshells, the one with the highest N value. So these are in the outermost. Okay, so if we look at all the N values in our electron arrangement, electron configuration, right? Remember the number at the beginning, that's the N value. So we have N value of 1, N value of 2, N value of 2, N value of 3, N value of 3, N value of 4 over here. That's the highest N value. We have 1 electron in it. We have 1 valence electron. Right, so we can determine it that way. If we write our noble gas configuration, right, that valence electron is what's left over here, right? That's your outermost electron. And all things being considered, that is the most important electron when it comes to the chemical characteristics of that atom, right? The valence electrons will dictate chemical bonding and chemical characteristics. So you can do that with pretty much any of your elements on the periodic table. We can write out the full electron configurations, or we can write the condensed ones, right? If it's not specified which one to use, you can use either. If it specifies full or condensed, make sure that you follow the rules. If we take a look at the actual now periodic table to help us figure this out, okay, we're going to use a fresh one here at the bottom, and we'll show you how that Christmas tree diagram need not be memorized. Okay, so here's a basic periodic table. We can separate this periodic table into different blocks. And we'll try to color code these as we go across. So the blocks of the periodic table. So the first one I'll highlight will be in blue. This one here is called the S block. And this actually also includes helium over on the right side. We have another block in green, which will green over here on the right side. Okay, and this is called a P block. We have a block in the middle, and we'll do this in purple. This is called a D block. And then we have the block underneath in orange. And you can maybe guess what we call that one. That's called the F block. Okay, so we've seen the S, the P, the D, and the F before, right? Those are the sub-levels. And different parts of the periodic table actually represent those different sub-levels. So for example, right, our S block starts over here, right? So we know in our electron configuration, we have already the S, the P, the D, and the F. But what about the principal quantum number N? Well, that is actually just the group number. I'm sorry, the period number. So if I have, for instance, this is my first period, second period, third, fourth, fifth, sixth, and seventh. Okay, so for instance, if I'm looking at, again, potassium, there's K, the one we did previously. We'll highlight this in yellow. Okay, the way that I use my periodic table to help me figure this out without having to memorize that Christmas tree is as follows. I'm going to start always at the top left and I work my way across. So in order to get all the way to the end, I have to go through the 1 S block. So I say 1 S, and how many elements do I have to go across? 1, 2. So that's 1s2 gets me to the end of the first period. Then I go to the next period, which is the second period. I have to go through the S block. Okay, so I go through 2s, 2 of these elements. So that would be 2s2. Okay, 2s2 gets me through lithium and beryllium, right? The 2s, and I go through 2 elements. Then I get to the 2p now. And how many elements do I need to go across? 1, 2, 3, 4, 5, 6. So 2p, 6 gets me to the end of the second row. Then I get to the third row. So this will be now my 3s. I have to go through these 2. So 3s2 gets me to the end of the S block. So that's 3s2. Then I get to the p's over here, all the way here, and I'm still in the third row. So 3p, 1, 2, 3, 4, 5, 6. So 3p6 gets me all the way to argon. And then I'm in the fourth row, S block. Potassium is the first element. So then I end up with fourth row, S block, first element. That's potassium. Same electron configuration as using the Christmas tree diagram up here. And what I can also do is I can also come up with the noble gas configuration. I know where potassium is. I just go backwards and I find the noble gas before it, which is argon. I do the same thing. I put argon in square brackets. Okay, I guess that takes care of all of this, all of the first 18 electrons. Okay, then I'm at the fourth row, S block, first element. So that will be 4s1. Same thing. Okay, and I don't have to memorize anything. I just need to know what the S, the P, and the D blocks are on the periodic table. Okay, so that's a quick way to come up with the electron configurations. If you don't want to memorize the Christmas tree. So there are a couple wrinkles to this, however. Okay, so for example, if we talk about, if we look at an element in the D block, all right. So let's say, again, with we'll choose something in the fourth row. So let's say I'm looking at let's say I'm looking at, let's do iron Fe. Okay, so I have 26 electrons to configure. Following the same rules, okay, I can work my way across from top to left, left to right, and work my way down. So for Fe iron, I have my 1s2, my 2s2. Okay, so 1s2 gets me all the way across, 2s2 gets me here, then 2p6 gets me to the end of the second row, then 3s2 gets me here. Okay, 3p6 gets me to the end of the third row. Now I'm in the fourth row. I have to go 4s2 to get to the end of the S block. Okay, and now I'm into the D's, right? So this is the D block that iron is in the D block down here. And how many elements do I need to go across into the D block? Well, I go 1, 2, 3, 4, 5, 6. Right? So I'm 6 elements into the D block. So I would be saying D. However, when you number the D block, it's 1 less than the S, right? So if in that row, the S was numbered 4, so this is 4S for potassium, and that we started off that row with, well, then the D in the same row is numbered just 1 less. So instead of being 4D, it would be 3D, and then we said 6. Okay, so we can say then that the D is numbered 1 less than the S and the P. In the same row. All right, so let's do another one because we end up with, this is our full electron configuration for iron. Okay, this is Fe. If I did my condensed configuration, again, the noble gas that came before it would again be argon up here. Okay, so we have our argon in square brackets. That takes care of the first 18 electrons. Then I still have my 4s2 and then 3d6. Okay, if I do, let's just do another one in that same row so we can kind of reinforce that point. If I do, let's do in green here, we'll do bromine. So bromine is this thing. So bromine has a total of 35 electrons. Okay, so if I go through the same process. Okay, 1s2, then 1s2 gets me to the end of the first row, then 2s2 gets me to the end of the S block second row, then 2p6 gets me to the end of the second row, 3s2 gets me to the end of the S block in the third row, then 3p6 gets me to the end of the third row altogether, then 4s2 okay, gets me to the end of the S block in the fourth row. Okay, so right here is where 4s2 ends. And now I'm in the D block now, right? I have to go across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of this would be D10. And I'm in the fourth row. Remember now the D is numbered 1 less than the S. So if this was 4s, this would be 3D. So that would be 3D10. Gets me to the end of the D block. So 3D10. And now I'm back into the P block over on the right side, over here now. Let me highlight this in green. Okay, this is I'm back into the P block. I'm now in the fourth row, and the S and the P are always numbered the same. So this was 4S down here. This would be 4P. And then how many do I need to go across? 4P, 1, 2, 3, 4, 5. So 4P, 5. And that would be the electron configuration for bromine. Again, that's the full electron configuration. To write the noble gas configuration, you can find the noble gas before it, which is argon in square brackets. And then I have our 4s2, 3d10, 4p5. Okay, and now if I want to determine a number of valence electrons, okay, those are the electrons in the highest n value, which in the case of bromine is the fourth energy level. So I have 2 electrons in the 4s, 5 electrons in the 4p. 5 plus 2 is 5. So I have 7 valence electrons. Right, the valence electrons are in the outermost energy level. Sub-level in this case is the 4th energy level. Both the S and the P belong to that energy level. So the periodic table can be used again. It's a very important tool, very predictive tool we can use. If you're wondering, when we get to the F block is just numbered 1 less than the S. I'm sorry, it's numbered 2 less than the S and the P, as opposed to the D's that are numbered 1 less than the S and the P blocks. Sometimes you'll see the electron configuration, for example, like for these, just to show that the valence electrons are kind of all together. Sometimes you'll see it being written as, in this case, you'll see argon, maybe 3d10, and then you have your 4s2, 4p5, just to kind of lump them together to show still that you have your 7 valence electrons. Okay, just keep in mind that if all else fails, you look at the number of electrons in the highest energy level, right? Which in this case is the numbers, the big numbers, so the first number, so the n equals 4 in this case. So we just count the 2 and the 5 together. That gives us 7 as our number of valence electrons, which, by the way, corresponds to the group number for bromine. It is in group 7A. Guess what? It's got 7 valence electrons.